called limited results. So let me recall the following proposition from lecture 2. Lectures are supposed to be interconnected. There is a reason I did all that extra material in lecture 2. It wasn't entirely just motivation. There was also some results, 2 results that I need to use from lecture 2. Okay, so let me recall them, you probably forgot it. So it says that if, so this is proposition 5.13 in lecture 2. It says that if G is CS, CS function on ZP with an extension of QP, and GH tilde is the partial Taylor expansion. Not following all computation, N was greater than equal to 0. Sorry, H was greater than equal to 0. H was the size of the ball. Was a French natural number. For each French natural number, there was a partial Taylor expansion, GH tilde, which was built out of the functions that were in the definition of CS. Okay? This is a polynomial times a characteristic function. On each ball, it's a polynomial. It's called a locally polynomial function. Looks like a Taylor expansion. Then the conclusion was GH tilde converges to G in CS. We'll take S3R by 2 soon, that's why I'm not writing CR there. Okay, remember CS was some class CS functions on ZP, essentially but not quite S times differentiable functions with continuous derivatives. The rest. Any function in CS has that property, but not every function with that property is in CS, right? That we saw some examples. So it's a bit different from the analysis where the definition is essentially that CS is S times differentiable function. So that's a small subtlety, but anyway, these partial Taylor expansions converge to G. Remember, we had defined a valuation on CS, which I won't recall, but it was essentially the soup of the into the Mahler expansion summation in x choose n, and the soup of the coefficients, soup of not the coefficient, but soup of n to the r or n to the s, absolute value of a n, getting absolute value of a n. And the soup of those are going to 0 in this for every CS function, so you can take the largest such number, essentially, and that was the evaluation, right? So in that valuation, we have this, the last theorem I did in that lecture. Okay, and then the claim is that the difference, GH tilde minus G goes to 0. Okay, so this is one result. Okay, so this is generalities. We're going to fix some specific functions. So this is functions on ZP. Suppose we take a function on QP. Because remember in the Banach space you had functions which were on QP. Right? And on ZP they had some property, and then the G1 of Z had some other property, right? But these are all functions with properties on ZP. So we can use those things, but we start with a function on QP. And suppose it belongs to DK. I won't write the definition of DK again, but it was functions which were CR by 2 on ZP when you shift to ZP, and Z to be R, now this R is K minus 2, Z to the r g of 1 over z extended from a function of zp minus 0 to a CR function, CR by 2 function on zp. Yeah. No, there were functions on QB to E. So there are functions on roughly on the whole globe, Earth, where in the northern hemisphere there's CR by 2, in the southern hemisphere there's CR by 2. Right? So roughly you should think of it like that. CP is like a, I don't know if that's a very good analogy, I haven't thought about it, but that's the way I think of it. Okay, so start with such a function. The claim is, I won't have time to check these small claims. So you want to get a function on ZP. So what you do is you just multiply this by the characteristic function of ZP. And you can also multiply it by the characteristic function of 1, the complement of ZP. P. So the claim is that both these functions also belong to PK. Here's a little argument is given in the notes. I think they were circulated last evening. People see that? Yeah. So you can look in there, and this argument is given there. So let me not get too much into minor things and stick to the main points. Learning from Carol in the main lectures. Okay, so what does this do? So now we can apply this result to that function. So by proposition, above the side, get that G of 1 CP belongs to congruent to H tilde modulo pi E theta AL. So we can approximate G times 1 ZP, which is now a function on ZP, right, by one of these GH tilde functions with S equals R by 2. Okay, so this is a little bit of hand waving going on here, but I've tried to give some details of the proof of this right below in the notes. Maybe if I write it now, it will take too much time. So the issue is that there are two kinds of convergences. One is with respect to this lattice, and one is with respect to the lattice for CR by 2 functions. Okay? So this convergence means that the difference belongs to pi to the n times the lattice for CR by 2 functions. Okay? That's what this convergence means, as for arbitrary large n. And this convergence means that the difference, this congruence means that the difference belongs to pi times this lattice. So they're two different lattices. But a small check, which I've done here, shows that that lattice is contained in this lattice. Okay, so does everyone understand what I'm trying to say? So if the difference GH tilde minus G belongs to theta sub R by 2, that lattice, since theta R by 2 is sitting in this lattice, that's a small check, which I will say orally, then the difference belongs to pi times this lattice. So the difference belongs to pi times that lattice is sitting in this lattice, then this difference will belong to pi times this lattice. If the first lattice is sitting in the second lattice. And if you remember, we had showed, one of the results was, I hope I mentioned it, that there were these locally polynomial functions, E, I, K, R there, but R is R by 2, so E, I, K, R by 2. We had shown that these functions form an OMB, orthonormal basis of CR2 by function, that we had mentioned in that show. Now if you look at the power of P occurring in those locally polynomials, it's a certain power, and the power is exactly P to the floor of L of I, R by 2 minus J, if you look at E, I, J, comma, E, I, comma, J, comma, R by 2. Anyway, there's a certain power of p there. This is with the wave function I plus p to the Li z p. And that power happens to be just a little bit bigger than the power that one needs to be in theta. And this is by this lemma 6.3, which was mentioned at the end of the talk. No, it was not mentioned at the end of the talk because I ran out of time, but it was in the tutorial. So there were these no-free polynomial functions, e, I, j, comma, r by 2, and each of those lies in theta kl by that lemma. I think that lemma was done in a lot of detail. Right? It was something like the following kind of function. Yeah, so p to the h minus 1 r by 2 minus j, where you have the h ball, so h is L of I here. So p to the L of I minus 1 times r by 2 minus j. There's a function of I plus p to the Li z p. Those things were in the lattice because of that lemma. Okay, so they were integers, and the EIKRs have a slightly smaller power of p in them. Okay, so that's a little check that's there in the notes. I will not check that. Okay, so putting those together, you can move from convergence in that CR by 2 lattice to convergence in this theta KL lattice. This is actually not explained in our paper, and I think it should be added in at some point. Okay, so, but if you were a non-expert, you can just think, oh, this is getting close to this, so the difference has to be a high power of pi times the unit ball. The question is, what's the unit ball? Right? There are two different unit balls. One unit ball is something. Okay, so here's another lemma. So notice that these go up to floor S, and we want to actually go up to a slightly larger number. So let me make the following lemma 8.2 in the paper. This is option 5.13. 9.2 in CG. It says the following, that you can actually extend this to some higher number of derivatives in a fake way, because these terms are all 0 in pi times the lattice. Okay, so they will not affect this kind of numbers. Okay, so let me say that. So say G belongs to CR. This is also a generality now. We're going to apply it to G1ZP. Let me just call it G here. So this G is different from this G. Okay. This G was a fixed GP, which I'll define in a second. But this G is G1ZP for that obscure G. So suppose this has continuous derivatives. Maybe this is not worth mentioning. It's a technical point, but let me just say it. Order floor r by 2 plus 1 all the way up to some t for an integer r by 2 less than t less than r, and set. So notice I put a tilde here 2 lectures ago with a bit of foresight. Who puts a tilde on something? There's no reason. The reason is that I want to drop this tilde and modify GL tilde to GH. So GH tilde. So what is this modified function GH? Essentially the same, it just has a few more derivatives. So let's go all the way up to t this time. J priori is larger than, not a priori, but is larger than 1 by 2. M Z minus M J over J factorial. There's a distinct bias of this blackboard towards short people. That's why Carol's lectures are so good. Anyway, so yeah, we have this. Then for large H, we have the same GH tilde of Z is congruent to GH of Z. This is going to be 0 again. Mod I times the lattice. I won't write pi E every time, I'll just write pi. So pi with pi E. So these are some technical points, but I'm just trying to go in order and go a little bit slowly. So turns out that it's easier to work with functions which go to a slightly higher, more derivatives are included, but because we want to do some algebraic manipulations. But this is not a problem because it turns out that for these large derivatives, these things are 0 modulo pi times the lattice. These things and these Gaussian functions are 0 times pi times the lattice. Okay, this again uses that lemma, very important lemma about what the rings of integers are. Okay, let me skip the proof of this again. It's just a technical point, and I could have come straight here. I mean, the corollary of this is that G is congruent to GH, not just G congruent to GH tilde, modulo pi times the lattice. I strongly advise you to look at some of the proofs. I tried very hard to write them out in complete details in the notes. But these are technical points and not really the main point, so let me skip these. So corollary of the proposition and that lemma 8.2 is that if you start with the G in dk, then G 1PZP, sorry, 1ZP is congruent to GH mod pi times theta k. Theta k was the lattice I defined in the Banach space, right? At the end of last lecture. With the image of induction sin k minus 2 OE squared. On the left, we had a uniformization of the Banach space by compact induction space. You get a rational structure. You take the integral structure in that compact induction space and push it over. You get an integral structure on the right. That is the lattice in the Banach space, essentially up to completion.
Maybe for large h here.
For large h. Okay, so what's the plan now? The plan is the following. Should I give you the plan or should I suppress the plan? No, maybe I should. So the plan is you pick an intelligent, because you know this looks very abstract in general. Let's get to concrete things. You pick an intelligent. Intelligent will become a bit clearer. What does intelligent mean? Intelligent function G. Clever function of the form summation lambda I think I had talked about such kinds of functions. Z minus Zi to the n log L Z minus Zi. Right? So you take this polylog kind of functions, one of them times the log, take a linear combination of them with some coefficients. The centers are shifted a bit, Z minus Zi, log Z minus Zi. We had studied these kinds of functions, right? We had studied CR by 2, if n is bigger than R by 2, etc. Right? Okay, so we're going to start with such intelligent functions. Intelligent means we have to choose these constants very carefully, the zi's and the lambda's. That's where the number theory comes into the picture. Okay? Leaving analysis and doing some complete number theory with, well here let me just be general, summation lambda I, Zi to the j equals 0 for all 0 less than j less than n. Okay, this n is going to be bigger than R by 2. So Then this function is CR by 2. Notice that this implies that this polynomial summation lambda I z minus zi to the n is equal to 0, right? Because all these kinds of finite sums, they appear the coefficients here. This is actually just a constant polynomial. Sorry, the degree. It's just 0, so that it's actually 0, not even a constant polynomial, it's a 0 polynomial. So the degree of this polynomial is minus infinity, which is less than r by 2. Okay, so let me say that we're going to pick such a function in dk. So n will be larger than r by 2, so that it's in dk. And remember we checked that this is in dk if some sums vanish. Remember this? Some sums vanish. I showed you that this function was in dk because if you put 1 over z there instead, do some manipulations, then it's the other condition of being in dk is satisfied. So we're going to do something a bit stronger. We're going to choose such functions where these sums, remember the degree of some polynomial has to be strictly less than r by 2. We're going to even make it 0, make it the 0 polynomial. So overdo things. Maybe this paper can be fine-tuned by being a bit more subtle about such things. But so we just make the degree vanish. So we'll see some examples of this kind of thing. So then what do? We write this function g as g, this is a function on qp, right? qp to e. The zi's are going to be in cp, so this is a function on qp to e. For example, these numbers are in e, and then you can plug in, right? We made log L be defined on powers, these things were defined on qp. Remember, e went to the ln variant, for instance, right? Function on qp. So you can break up every function in the following form. This is just a motivation of what's going to come before I do 1 hour of a lecture. We already said that this belongs to dk, and this belongs to dk. That was the first remark over there, right? Both of these functions belong to dk. We break them up into the zp part and the qp minus zp part. And by this result up here, this part is congruent to gh, right? The 1cp part is congruent to gh. And this will be gh with t equals n minus 1. We'll apply it with t equals n minus 1. And just a technical point, there was some abstract t here. There was an n over there, so we'll apply it with t equals n minus 1, but that's important. And the main point, which I'm about to do next, is to show that this function is also congruent to G2. This is all modulo, and I know space, so I'm going from right to left. Switch to Urdu mode right now here. Pi theta kl. Okay. So this is need to show. We already have up to here. This W means width. So we want to show that you can further get down from GH, where H is very large, like G10 to G9 to G8 to G7 up to G2. You can always get down to G2. Okay, so this is going to be the next step. And the other thing that we do, but we will not show in these lectures or even talk about, is we show that this part is 0. Modulo pi times the lattice. So these functions outside CP, they're going to just be in pi times the lattice, whereas this will not be 0 pi times the lattice, but it will be congruent to a certain function G2, where G2 is defined over there. Okay? So ultimately, we will come down to some kinds of functions like this, with h equals 2. And these kinds of functions look like functions which are in the images of certain Heck operators. Okay, so that's where the Heck operators will start entering the business. And ultimately, when we have Heck operators, then we have these phi r lambda etas, and then we can invert those and get the Galois representation. Okay, so that's the strategy of what we want to do. So plan need to show this, won't show this, will not show. Doesn't mean it's not true. This is 0 except in one case where it's not 0. No, it's not good about that. So essentially that term is 0 and this term comes down to G2, and this looks very much like a function in AB1 equation. This is how head operators are going to enter the business. I'll come to those details at the end of the lecture. Any questions so far? I hope that at the very least you can see that this is high school mathematics. You're looking at just partial Taylor expansions, various congruences. Except you're doing everything on QP or ZP and things like that. Okay, so this is the plan. And from here we have to still proceed and use Deva-Hori on PLLC right, to conclude. I'll explain that at the end of the talk. But for now, this part of massaging these functions, this is what we want to do. Okay, so here's the lemma. So lemma 8.3 says the following. So let a by 2 less than equal to strictly less than n maybe, or less than equal to n, less than equal to r, less than equal to minus 1. Let C naught belong to QP, QPB. Let x belong to, let x be a rational number, with x greater than equal to minus 1, and equal to minus 1. If x plus the valuation of L is greater than equal to r by 2 minus n, so some technical condition relating to valuation of the L invariant and all these numbers, then you have the following congruence. Oh, I need some more notation. Yeah, so Gj a plus alpha p to the h minus 1 is congruent to Gja plus alpha p to the h minus 1 Gj plus 1a plus alpha p to the h minus 1 n minus j minus 1 a over j factor, n minus 1 by j factor, modulo pi times the lattice. I forgot to write modulo. Oh, not pi times the lattice. I checked it. There's no lattice here, there are no functions. This is just a congruence of two numbers, and the quantity is p to the h minus 1. Ready? Modulo p to the h minus 1 r by 2 minus j times pi. For all h greater than or equal to 3, j less than or equal to n minus 1, a between 0 and p to the h minus 1, and alpha between 0 and p minus 1. Okay, so the statement is a bit long. But if you take j to be 0, for instance, then this is just the g function, and you're saying that the g function has a Taylor expansion, a partial Taylor expansion, you can truncate it up to this power. Okay, so this is what this statement is saying. And you can do the same thing for the derivatives, first derivative, second derivative, up to the n minus 1 derivative. Okay, so g is fixed as a function here. Oh, I forgot to say what g was. Sorry, that's the main point. I tried to make it more clear than my notes because I wrote the function first and then all the notation later. I could have read the notation first and the function later, but I forgot to write the function. So this g here is not defined. And for g, nobody's asking any questions. I'm getting a bit worried. G of z equals p to the x. This is a function. It's one of the factors of that kind of function. Z minus z naught to the n log L z minus z naught. For this kind of function, you have a partial Taylor expansion modulo item. This is one of the terms in this function. Questions about this statement, the notation? So you have a function which is a typical one of these functions, right? Remember, g is a sum of such functions, right? But we want to somehow show that g is common to gh for large h, right? So oh, we've already done that, but we want to come down from GH to G2. So to do that, we need some results here. Notice H is greater than 3. Anyway, so we want to come down from GH to G2. To do that, we need to bring each of these functions down from GH to G2, so to speak. There are many components, and we want to bring each one of these down to a G2. So I'm analyzing just one of these terms, and to do that, there is such a congruence. Now this congruence is sort of the main point of this lecture. I mean, not the main point, but one of the main points of this lecture. And I actually spent a lot of time on such a congruence in lecture 2 or lecture 3, lecture 3. Right? We did lots of estimates on valuation of L, 1, things like that. So very similar kinds of results with a bit more care. Very similar techniques with a bit more care giving this thing. So this is 1 or 2 pages in the notes, and you can look at them. Just pure analysis of some kind, analyzing valuations of the log function and things like that. We did quite a bit of this in lecture 3. Probably the only proof I did is 4 lectures so far. And very similar techniques allow you to get congruence. Here's a corollary of that. Same notation, Gj of a plus alpha p to the h minus 1. It's multiplied by the following polynomial function, z minus a minus alpha p h minus 1. The j, 1a plus p alpha plus alpha p h minus 1 plus p to the k zp. Now I can put the lattice in. Congruent to exactly the same expression over there, Gja plus alpha ph minus 1. I'm trying to write some of these little bit technical points down explicitly to see that it's literally playing with some partial Taylor expansions, this business. Alpha ph minus 1, n minus 1 minus j, please make sure I'm copying from there correctly. Gn minus 1 of a over n minus 1 minus j factorial times, should have some space, and over here, z minus a minus alpha ph minus 1 to the j, there's a function again, 1a plus alpha ph h minus 1 plus p to the 8tp. Modulo pi times beta k. So if I had written this statement straight away, it might have been a bit confusing. So I wrote first a congruence between two numbers. It's just a number. Some derivative at some point is congruent to the partial Taylor expansion modulo some high power of p, right? And now I multiplied that congruence by a characteristic function or a polynomial and a characteristic function on both sides, right? So that means that if this number times that polynomial times the characteristic function was in the lattice without the pi. If this number, this high power of p times the characteristic function times that polynomial first and characteristic function was in the lattice, then you get that congruence immediately, right? By putting a pi everywhere. Okay, so you can show that this high power of p times the polynomial over there times the characteristic function is in the lattice. And since this difference is pi times such a thing, it will be in pi times the lattice, right? It's an immediate corollary of lemma 6.3 because we know that this power of p, this was done in the tutorial, this power of p times that polynomial function times the characteristic function was in the lattice. So with a pi in front, it's in pi times the lattice. So the difference. Okay, so this is just immediate from lemma 6.3. Tutorial. Tutorial 2. Okay, let me write too much details. I said it twice already. Let me not write it down. Does anyone want me to write that? Can you follow? Any questions? Exact application of lemma 6.3. Okay, so now in the notes there's a couple of pages because we didn't prove the lemma yet. It probably is obvious from the lemma, from this lemma 8.3. But there are a couple of pages of proofs of lemma 8.3 which people who are interested and want to get into this kind of thing can look at. It's very nice estimates of polynomial set log functions. It's time to do some lower bounds usually of the evaluations of such things. Okay, so great. So that is this corollary. Now I'm going to use this corollary in the next corollary in the next lemma, which was lemma 8.4. So same conditions, but to be pedantic, slow things down, let me repeat. K over 2 is less than equal to n, less than equal to r, less than 2 minus 1. Z0 belongs to CP. X belongs to Q, rational number. X greater than equal to minus 1. And X plus the valuation of L is greater than equal to r by 2 minus n. The condition. Then if g of z, this time I'm remembering to write the function down, will be x z minus z0. Remember, we want to apply it with z0 equals zi. We're taking one of the many functions going to the definition of g, the component, the g function that we wrote up. This is what I just listed. N Lz minus z0 1 Cp then G is congruent to, I'm just wondering if there should be a 1 Cp there. Maybe there was, but I'll go back to it. So if you have such a function, then GH is congruent to G2. Here. This is what I was saying, that you take this function on QP, multiply by the exit function of ZP, and then you can approximate that by some GH, by some generalities. So from Kohlweis's paper. But then you can actually go all the way down from GH for large H to G2. Sometimes to G3, but let's not worry about those cases. You get down to G2. Okay, this is what I was saying, the plan of lecture. This is the lemma which says we can get down to G2. So let's see how this lemma, or rather that corollary over here, can be used. I'm going to give a slight sketch of this. Not trying to prove things, but let's see how lemma 8.3 can be used. Actually, corollary to lemma 8.3, which formula is still up there, can be used to prove this. Okay, there's some remarks here in the notes about everything is well defined, etc. And when you write something like this, let me not get into it. But the first page of this is checking that some things on both sides of the congruence are in DK. Okay, so let's do these algebras. So let me back up a bit. So here's G. So already, so recall. So proof. Proof as a sketch of proof. We know that G, we've already done this part. Let me just recall it again. Is G H tilde of Z. And we've come down from GH, not come down, but we massage GH tilde a bit to write it as GH. 1 pi times the lattice. We already know this much, and we want to go now from GH to G2. Okay, so assume H is greater than or equal to 3. So that we can apply this corollary, which also had H greater than or equal to 3 in it. So secret H greater than or equal to 3 here. So to raise because it was in lemma 8.2, or it's lemma 8.2. And let's do some massaging. So first we have to write the Taylor expansion of GH again, so let me do that. Recall that GH of Z was, let's go with slowly, A equals 0 to the H minus 1 minus 1. You just check your notes and make sure that I wrote usually H minus 1 there. Oh no, I wrote usually H minus 1, and now I'm writing usually H minus 1 because I'm breaking this in a slightly different way. So that's why it's confused. Let's break it up like this. Gj A plus alpha pH minus 1 over J factorial. Z minus A minus alpha pH minus 1 J. And that's a function 1A plus alpha pH minus 1 plus P3 and CP. So if you look at the definition of GH, which I raised a few minutes ago, the sum was on H balls, right? PV H balls. But here I'm doing PV H minus 1 balls. Not PV H minus 1, it's still PV H balls, but I'm breaking the representatives up a little bit, right? So these representatives, which were just A is going from 0 to PVH, minus 1, lower, minus 1, right? You can rewrite them in this way. I've broken them up a little bit by putting this alpha term in. Okay? Okay? So by the corollary, I'm now going to use that corollary over there to massage some of these terms, so let's do that. So this is some algebraic manipulations using that corollary. Into the h minus 1 minus 1. Some alpha is equal to 0 to p minus 1. And then I have to now be really careful here. Make sure that I can write these in various columns. Let me write it and then be quiet for a second. Applying first, this is the definition, right? I'm applying this with j is equal to 0, that corollary with j equals 0. If you apply that corollary with j equals 0, what happens? Right? We have all the same things here with j equals 0. If you apply that with j equals 0, then you get g0a plus all these terms, g1 up to gn minus 1a, right? Minus 1 factorial. And there was already a 0 factorial here, so that's why 0 factorial, which is common throughout this. And then there's some new factorials coming from there, which I wrote as 0 factorial, 1 factorial, 2 factorial, n minus 1 factorial. I'm going to start grouping them in a different way. So what I'm doing right now is I'm writing the definition, then I'm applying that corollary to each of the terms in the definition. Okay, and then I'm actually going to sum over columns. So that I'm going to group in a different way in a second. But I haven't started doing that yet. But you're looking ahead. Let's do the first derivative. The first derivative is g1a 1 factorial, 0 factorial, same kind of thing, up to alpha ph minus 1 n minus 2 gn minus 1a divided by 1 factorial n minus 2 factorial. And here, there's a characteristic function, which is, by the way, this was not there. This was from the previous line. But here, there's a polynomial, z minus a minus alpha ph minus 1. Right? Because when j is 1, you have this thing also. Right? And I'm now applying this with j is equal to 1. If that with j is equal to 1, then you go up to n minus 2 in the alpha power. That's what I wrote here. The derivative is still gn minus 1. I'm collecting all the derivatives together here. And keep doing this all the way up to j is equal to n, I guess. And plus, so here you'll just have one term. And it's g, you see these powers are dropping. This is a dot dot dot. There's so much other noise on the blackboard that you can't see the dot dot dot. Yeah, so just keep applying that corollary. And what happens is here, for the last j, you get g to the n minus 1 of a over n minus 1 factorial. Right? J was going up to n minus 1, the n minus 1 n for j. This is this n minus 1 factorial, and divided by 0 factorial. There will only be one term when you start with j is equal to n minus 1. J is n minus 1, this thing should stop at n minus 1, right? So it's starting at n minus 1 and stopping at n minus 1, so there's only one term. And we have this. There's a dot 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 here, which I hope you can see, times a polynomial. Z minus a minus alpha ph minus 1 to the n minus 1. I hope you can see the difference between my h's and n's. Yes? And then a round bracket around the whole thing, a curly bracket around the whole thing. Okay, so that's this stuff. This curly bracket is this curly bracket down here. Okay, and then finally I have to write the function. And the function is times 1 a plus alpha ph minus 1 plus p to the az. Sorry, it's degenerating. It's really tough to write down. Okay, so I use this corollary and I just plugged in for each of the derivatives in that corollary. Okay, now you sort of sum along columns. Okay, so let me write the answer first and then we'll see why that's true. I can erase the corollary now because I've used it.
Maybe one small point.
Yes.
Over here we can see that n minus 1 factorial doesn't have any powers of p because n is small. That's why you can divide by it. Right? So while applying the previous lemma, there was only a single denominator, right? But here there are two denominators.
Yeah.
So just a small remark that all of those are tame. They don't have any powers of p, so you might as well divide by them. The first 0 factorial in the first line, the first 1 factorial in the second line, dot, all of those.
Yeah, they don't have powers of p, but I don't know why you're breaking them back. Anyway, n is less than equal to r, which is less than p minus 1. And so, yeah, none of the denominators, all those denominators are units. Yeah, maybe 2 because of pi times the lattice and things like that. Okay, come to this. Okay, so I'm claiming that this is equal to sum a is equal to 0. Let me write it first because at the board you will see most of the things that you're writing. Very different perspective. Alpha is equal to 0 to p minus 1. I'm claiming you get this. G of a, 0 factorial over 0 factorial, plus g1 of a, 1 factorial, 0 factorial, z minus a, plus gn minus 1a, z minus a to the n minus 1 over n minus 1 factorial, 0 factorial, times 1 a plus alpha h minus 1 plus h. Okay, and how do you get this? This is by expanding z minus a minus alpha ph minus 1 with j as an alternating sum with binomial coefficients and some obvious powers of these things for 0 less than equal to j less than equal to minus 1. Okay. So what happened here? You can see that all the alphas have gone away. Right? There's some fake alphas now outside of the sum, but here there are no alphas. This was the main point of that, to get rid of the alphas in this argument, because somehow you wanted to go down from level h to level h minus 1, right? So we introduced these alphas to do that, and then we got rid of the alphas. You see a second, the alphas will go away. Okay, but before we go there, I'm claiming that if you expand this function out and collect terms, you get that identity. Can we see that in any particular case? I have some examples here for the second column, for instance. So many of the alpha terms are going to go away. So where's this term? G of A is 0 factorial 0 factorial. That's here already, right? That's here.
Yeah,
right?
it will cancel out.
And below that, there are no terms here. So we want to somehow get rid of this term.
This will
I
cancel
cannot
out
do
from
this
the.
on it's impossible. Yeah, okay, maybe this is a better perspective.
So I think the first alpha p to the power h minus 1 will cancel out from the second row, and then the
yes, very good.
higher
Thank
power
you so
will.
much. Very good. So you're claiming that this alpha ph minus 1
Will cancel out from the
will
next
cancel
row.
with this minus alpha ph minus 1 g1a 10 factorial, right? So this is one little observation. And if I had written the second column, which I have in my notes and done that, then three things will cancel. Okay, so basically the alpha terms are cancelling and you will get only these pure A things.
Maybe the
And
last
pause.
column.
Yeah, what about the last column?
Instead of the
So
second
this term
column.
I think is there. No, this term is not there. All of these have alphas in them, right?
Yeah.
This term doesn't have alpha, so you want to preserve this. That goes over there, right? And all these terms, we want to get rid of them. So there's alpha ph minus n minus 1 with no power of an extra alpha. Here you put this alpha ph minus 1 with that, right? So you get a like power of alpha ph minus 1. Gn minus 1a will be common. Yeah,
Sir.
then there will be, anyway, there's some binomial expansion here, collection of terms, and yeah.
Yeah, so we looked about what would be the coefficient of alpha p to the power h minus 1 power.
Speak louder in the.
Yeah, so alpha p to the
AC
power.
here.
Yeah, alpha p to the power h minus 1 power k g k a. So in general, what would be the coefficient of alpha term? So you want to say that
Are
all
you
alpha?
making a comment or you asking a question?
No, I'm giving some remark.
Giving
That what would be the general term alpha term?
Yeah.
So you want to show that all alpha term is going to be 0, right? So if you look at the coefficient of alpha power alpha times p power h minus 1
Yes.
whole power k g k a, so that formula is sum over. So can I write the formula then?
It's okay. It's
Yeah.
quite fine. Yeah. You
Yeah.
can.
So-
I mean, saying that out loud is more confusing. I think what one just checks is that some alternating sum of these things with a like power of alpha, they will die. Okay, and if you're getting a bit confused, I did some examples in the notes. I didn't write the second column here, so we just did the first column, thanks to Shivash. There are 3 terms in the second column, and I think I did that G2A. Oh, yeah, okay. Fine, so we get this, and finally, because this term is independent of alpha, I can move the alpha past this Taylor expansion to come over here. Right? So this is the same as the sum A is equal to 0 to p to the h minus 1 minus 1. Notice we managed to drop down to h minus 1 at 0 point. And we made a slight typo there. That says sum from A is equal to 0, not 1. I'll read my handwriting and clear 1 there. Starting from 0, 0 to n minus 1, gja, z minus a to the j, over j factorial, 1. Okay, so again, if you move this alpha all the way over here, right? And what is the sum of these characteristic functions over here for all alpha? It's exactly this function. 1a plus e to the h minus 1. break this h minus 1 ball up, like it's like breaking a p ball into p square balls, right? You break a p ball into p square balls, h is 2, let's say. This is the way you do it, right? Well, this is great because this is exactly the definition of gh minus 1. This is the independence of alpha. Sum is, you just move the sum past and collect all these smaller balls into one bigger ball. H balls are a bit smaller, h minus 1 balls are a bit bigger. Right? So you collect them all into one slightly bigger ball, and this is gh minus 1. All mod, I'm not writing it, but mod theta k a. And remember, we could use this converse in the probability each time as long as h was bigger than equal to 3. Okay, those estimates that h was bigger than 3 is not so clear, I'm just telling you, but it comes up in the proof of that long lemma. And you really need h greater than 3 in many of those estimates. It's all very subtle, it's just you cannot be a little rough here. I mean, why 3? It's a random number. You will see in many of these estimates you need to assume h is greater than 3 when you do things. So now if you reiterate this procedure, you went from gh to gh minus 1. So from g10 you can come to g9, from g9 you can come to g8, right? Finally you can come to g3, g3, and then you can use it one more time because you're allowed to use it for g3. So g3 will be counted g2, right? gh is counted gh minus 1. So we're reiterating this thing. Reiterating for h greater than equal to 3, you get that gh is congruent to g2 mod by everyone can do the binomial theorem, so that's why I spent a little time on this step of the argument. Okay? You have a partial Taylor expansion, and then somehow you collect terms and things and come down to the g2 function, which is not such a complicated Taylor expansion. And in this business, basically these are the ones that show up. I erase some of this, and I'm going to erase this now. Okay, so far what have we done? We have started with a function g on QP, which is a sum of lambda i's, z minus zi to the n's for n large, n r by 2, times log L of z minus zi, sum of such a function, and we managed to show that g is congruent to gh is congruent to g2, right? Modulo pi times the lattice. So that was the plan. I had a plan here on this board. I said that the part on 1 CP that can be brought down to g2. The other part on QP minus ZP is congruent to 0, and that's similar but separate computation. We're not doing that. So this is the end of generalities for these are general arguments. This is for any lambda I and anything like that, any z naught, any z s, as long as n is bigger than average. Okay, so now let's get to apply all this to prove the main theorem. So section 2. So this is reductions of semi-stable Galois representation. So let VKL, I'll come back to this, okay? In the proof we need that you can get from G to G2. Try and remember this whole course so far was trying to introduce certain functions G, which can be brought down to G2 modulo pi times the lattice. And these functions G are actually going to be 0 in the Banach space, because if you remember, these kinds of sums of logs functions were the denominator of the Banach space, right? So they're 0 in the Banach space. On the other hand, they're common to something which looks like non-zero. So we're going to exploit this fact to finish the proof. But let me now state the theorem, because I actually didn't state the whole theorem, and I should have stated in the maybe in lecture 1. But here we now finally have that square again. So that VKL, this VKL has been coming as motivation in many things. So this is a two-dimensional, semi-stable representation of the Galois group of QP of hot state weights There are some technical terms, but you can just think of it as the weight is K. This is, by the way, if you take a Gall representation, many of you know modular forms. If you take a Gall representation attached to a modular form on in Sk gamma naught P. Okay, Sk, so weight K form, but the level is P. And you restrict the Gall p-adic Gall representation, P is on the right, to G to QP bar, G to E. You restrict it to the Gall group of QP, you get a local Gall representation. That Gall representation is basically this. For some number L. The weight K is that K, and the L is the L invariant of the modular form at P. Okay, but I said everything I do in life is connected to modular forms, but there were no modular forms in this lecture. But people who like modular forms, this is basically the restriction of the local Gall representation. And I want to also say that Shauna's lecture, Arvind's lecture is there. He also was trying to do congruences with P new things. My lecture, Carol's lecture, they're all concerned with the same thing. This fact that P is in the level exactly once, there's no limit I can set P in the semi-stable case. All Gall representations at this point are semi-stable. So all these courses are connected. Those two lectures and the two courses. Anyway, so it has Hochstein weight 0 K minus 1 and L invariant L. So I'm not defining L invariant. It's just a black box for right now, but these kind of local Gall representations that P are parameterized by two numbers, the weight K and another number, not AP, there's no P for coefficient. AP, the P for full coefficient modular form is very boring in this case. It's often just plus minus 1 when the weight is 2. Not giving any extra information. But there's a much more subtle quantity you can attach called the L invariant. And it plays the role of the P for coefficient modular form. Anyway, I better not say too many motivational things, otherwise I would never say the theorem. Theorem, this is the theorem in our paper. Theorem. So version 2, probably there will be more versions in the archive. It's from earlier this year. So say the weight is not too big, not too small also. So let's say the weight 2 is a bit uninteresting for the reduction problem because this Gall representation is reducible in case it's 0. Reducible not P, it's always reducible. There's no question of irreducibility or reducible. Okay, but in weights 3 onwards, this is irreducible, and mod P may become reducible, or it may stay reducible. So what happens? Then BKL bar, the reduction, varies through an alternating sequence of irreducible / reducible representations of GPP, mod P representations. Given by the following picture. So there's some mark points. There's this parameter nu, which I'll define in a second. It's basically the valuation of the L invariant. But there's some mark points. So over here, the Gall representation is induction omega 2 to the R plus 1. R is K minus 2. Over here, it's reducible. It's mu lambda 1. I should have written this a bit bigger. Omega R plus mu lambda 1 inverse omega is this point. This representation. And here it's again, it's an induction. It's induction omega 2 to the R plus P. Over here, it's again reducible. It's an alternating sequence of reducibles and reducibles. The ending points depend on whether R is odd or even. So it ends at either half or basically negative points, but sometimes they go a little bit positive after half. So again, here there's a reducible representation typo in my notes. The inverse here. And finally, the last irreducible representation is induction. This is here. Induction omega 2 to the r plus 1 plus r over 2. For one time space to write this. E minus 1. If r is odd, this case is r odd. This case is r even. Okay, so I wrote everything more or less correctly, except I haven't defined some constants, so let me just define some things here. So this is Galois induction. We're on the Galois side now. We're talking about reductions of Galois representation, not compact induction. You have the Galois group of QP squared, you have the Galois group of QP, you have the fundamental character of level 2, which is the multi-character of the Galois group of QP squared. You induce it up to the Galois group of QP, you get a two-dimensional representation, right? These are these particular induced representations. Omega 2 to some large power. Okay, so those are the monthly representations that are coming out of the reduction of the Galois representation, which are of the irreducible kind. At some mark points, already thing. Here at these mark points, you get some sort of reducible representation, fundamental characters of level 1 with some unramified characters in front. U lambda was the character which took, it's a character of the Galois group of QP squared, QP now, not QP squared. Taking Frobenius to lambda, and inertia is going to trivial, right? Most of this representation, most of the character is trivial. But on Frobenius, it's taking Frobenius to lambda. I'll write that. Anyway, the various powers of fundamental to level 1. If you notice, the powers are going up on the first and down on this. Down on the first and up on the second. Omega r omega, then omega r minus 1 omega squared, until they stabilize to a like power. Okay, r plus 1 over 2. That's well defined because r is odd. So r plus 1 over 2 is an integer. You can take the integer power. This last case propagates even to infinity. So you get something reducible here that stays reducible. Whereas in the even case, this guy is reducible here, but then it stays irreducible with this power. Okay, so the ending is a bit different. Ends in either a reducible representation or an irreducible character representation. Just a small remark since it was in the abstract, this can be thought of as a zigzag conjecture. Okay, this is what's called the semi-stable zigzag conjecture. And you have an alternating pattern of these things, and I have made such a conjecture completely independently of the crystalline world, which we haven't talked about at all. And one of the ways you can try and prove that is to prove the semi-stable zigzag conjecture, and then take limits of semi-stable representation, crystalline representation, to get the crystalline zigzag conjecture with a similar alternating pattern. Okay, so I'm not talking about that. I said if time progress, blah blah blah. The last time I abstract. That was the if time progress part. We're staying in the semi-stable world. Okay, so what are some of these numbers? So the constants lambda I. In number theorists, you try and write everything down explicitly without any abstracting, like for some lambda I or something like that. It's not like that. The lambda i's are some fixed constants. Move a bit faster. With lambda I given by the following amazing formula: -1 to the I times I times the binomial coefficient r minus I plus 1 choose I times L minus, oh, I should have defined u first. We do that over here, sorry. Nu, what is this? Nobody's asking any questions, but there's some number nu, right? It depends on the size of nu. And I haven't defined what nu is. So what is nu? Nu is the valuation of the L invariant, basically. Write it here. So the valuation of the L invariant minus two numbers, HV minus minus HV plus. So these are partial harmonic sums which for some reason enter the picture. So HI is the partial harmonic sum. 1 plus half, where the number 3 is coming in, 1 plus I. B minus and B plus are the smallest, largest and smallest integers. Squeezing R by 2. R by 2 is either a half integer or an integer. So d minus and d plus are some integers which are squeezing r by 2, and then you have their partial harmonic sums. Subtract that from the L invariant, and then you get the valuation of. So now you see things are becoming more number theoretic. Right? So that's some number, anywhere between minus infinity and infinity. And depending on the size of the number, you get the Galois representation of p. What are the constants that show up? I started telling you those. So this L minus hb minus hp plus over p to the I minus r by 2. If 1 less than or 0 less than or 1 less than I less than r plus 1 over 2. Notice that this number is a unit, right? So these numbers are 1 minus r by 2, 2 minus r by 2, etc., right? So when the valuation of that is equal to one of these, then this quotient here is a unit, and you can reduce this mod p. It's actually, technically speaking, the mod p reduction of this number, which is a well-defined constant in fp bar. Okay, so that's how these constants are defined, and there's one case which is not included here, which is, this came up in Carol's lecture. He had x plus 1 over x in some places, and exactly the same kind of thing is happening here. So this last constant is not given by lambda is equal constant, but you have to solve some quadratic equation, and this is symmetric in this quadratic equation because the power of omega on both sides is the same, so it doesn't matter which root you put here. Okay, but this is given by exactly the same thing if I is equal to r plus 1 over 2 and r is odd. One particular case which adds 30 pages to the paper is to find this constant. Very tricky to find this particular constant. Okay, I think I won't define the other things because they've come up before. Fundamental character level 2, level 1, and this is the unramified character mu lambda, right? It's come many times. Okay, so now in 10 minutes I have to use the whole course up to lecture 3.5 to finish the proof of this, a bigger sketch of the proof of this argument, of this theorem. As I said, the idea of the proof boils down to this square. We don't know how to reduce the Galois representation. We take the Banach space, which I defined in lectures 2 and 3. We reduce the Banach space and started telling you a little bit about this, at least the ring of integers and things. And then use the Bahori mod p LLC to come up with the mod p Galois representation. Right? These are all the DKL bars. We're trying to find them. We don't know how to do it, so we go 3 ways around this square. Let me erase this. Okay, section 3, idea of the proof. So remember we had defined what it means to be an integer. This is like q root 5, and inside q root 5 you have some integers, z root 5, right? We defined the lattice theta kl. We have to reduce the lattice mod p, right? Okay? So it's enough to compute the reduction. When you want to compute reduction of Banach space, it doesn't make sense. You want to compute the reduction of a vector space. Compute the reduction of a lattice in the vector space. So we need to compute theta kl bar. And we recall at the end of last lecture, I had defined these subquotients. There was a map from induction Iz to G of sim k minus 2 e squared to, let me up right all the notation. We had a map at the level of Banach spaces. But we had reduced that map on mod P. Let me just go straight to the mod P map to theta k L bar. This map induced a map from induction IZG a to the I d to the r minus I, this character, to this subquotient f2I to I plus 1. And I said that if you analyze these subquotients, then we will get the reduction. 0 less than equal to I less than equal to r. So here is an example now. So we reached about page 35 of the paper with all the preliminaries. Now we have to actually do some computations. Use all this general theory to compute some of these subquotients. As I said, that if all but 2 of these subquotients are 0, often only 2 subquotients survive here. So this is a principal series. And therefore, by the Ivori mod PLLC, because the representation is reducible, if all but 1 survive, then this is super singular. And then by the Ivori mod PLLC, the representation is irreducible. Right? So you have to analyze this subquotient. So here's an example of this analysis. This is theorem 9.7 of CG. So let's look at the marked points. If V is equal to I minus R by 2, with I varying in a certain way so that you get all but the last marked point. So I equals 1, 2, up to ceiling of R by 2 minus 1. You can check that. So in particular, nu is less than 0. So I minus R by 2. Then the above map factors as, I write it here only, factors for pi r minus 2I lambda I omega I, which is isomorphic to the induction of a to the I d to the r minus I, compact induction I z to g. Image t minus 1, 0 plus the image of t 1, 2 minus lambda I. With lambda I given by this formula. Okay? Lambda I given by this first formula. So what's the claim? The claim is that we have a map to some subquotient, but it's factoring through this kind of quotient of a compactly induced representation. I mean, your induction representation. And these kinds of representation by the theorem ABC are exactly of this kind, a little bit of massaging here. Okay, let me not go through all the details, but let me try and show you that it's actually right, and then you can check that notation. So you see, this is great because often this representation is irreducible, and then this will be just things like that. Okay, so all right, so let's try and see why that's true. Sort of the main point of the last 60-70 pages of the paper, so spending only 5-7 minutes on it. I hope you get a flavor of it. So remember, we had to choose an intelligent function. Every time you want to prove something like this, you need to choose an intelligent function. Why intelligent function? So you'll see now. So choose the following clever function. Clever function g. So remember, this p to the x, when we're taking x to be minus 1, so we take 1 over p, sum I belonging to I, lambda I, z minus I to the n. So now I take zi to be I itself. We have to choose some central points, centers of these polynomials, z minus I. What is this set I? I is 0, 1 up to n. The minus n p. This is the indexing set. And what is n? I should have defined n first. For any n, but n is this number, r by 2 minus nu plus I, which, if you look at the definition of nu over there, is nothing but r plus 1 minus I, which is less than r, which is less than 2 minus 1. So the n's, so starting with a mark point nu, we manufacture an n by this formula, right? And this n happens to lie in the right range between k by 2 and r, so we can apply the general theory. Okay, and lambda i's are given by the following numbers with, I was going to prove that the existence of such lambda i's, because I won't have time. These are some numbers in ZP with lambda I congruent to 1 mod, lambda 0 congruent to 1 mod p, lambda p equals minus 1, and lambda I congruent to 0 mod p for all 1 less than I less than equal n. So this is the intelligent function. The intelligent function has the p-adic term over 1 over p, that's called the constants. The lambda i's are some integral elements which satisfy some congruences. These are the centers z minus I and log z minus I. So this is just all try and error, which was a bit painful in the beginning, and with some experience one could try and choose these functions a bit faster. So this is a function that we start with. The existence of such lambda i's, that you can find such lambda i's, is given in the notes. It's some van der Waals argument. Okay, so that's the yes.
This lambda occurring here, they are
Yes.
same, right?
Oh, sorry, no.
No.
Very good point. Thank you. This lambda is some final global constant at the end, and these are some local lambda i's that are coming up in the proof. Sorry about that. Yeah. Should worry about that in our paper. Somehow they're coming on the same blackboard here, but many pages apart. Thank you. Yeah, so these are the lambda i's, just coefficient of functions, and these are some lambda i's showing in the unramified characters of the Galois representation. Okay, last page of the notes.
Here they are
Yes.
in E, but here they are in P bar.
Yes, here they're in FP bar, and here they're in E. Very good point, yeah. Okay. So because the lambda i's are chosen in this way, the sums, the summation lambda I times I to the n, they actually vanish as lambda I to the j, because j between 0 and n, they all actually vanish. So this function is actually in decay. Okay, and then by the generalities, I said end of generalities, but by the generalities applied to this particular function, we get that G1ZP is congruent to GH tilde, which is congruent to GH, which is congruent to G2. We come all the way down to G2. Z. So this particular function can be approximated by its degree 2 Taylor expansion. Okay, whatever it is. I'm about to maybe write it down. Actually, not yet. Okay, now there's some. So this is what happens 90% of the time. In this particular case, in this theorem, it turns out that you can further bring it down to G1. So it turns out that G2 minus G1 plus G1, it turns out G2 minus G1 is 0 in pi cancel lattice. Okay, so you can come down to G1. Okay, so we'll take just 3 or 4 minutes extra. Should have erased what I went down there. Hope you remember it. So the 1ZP part is now down to G1, and the QP minus ZP part of G is 0. That's some other computation. So putting everything together, hence 0, which is GK, this is 0 in the Banach space. G is 0 in the Banach space. And BKL. Right? Because it's the denominator of the Banach space. On the other hand, it's also G1ZP plus GQP minus ZP, G1QP minus ZP, G1QP minus ZP is 0. The G1 CP part is just given by G1. This is congruent to G1, which is, by definition, something, but then with a little bit more massaging, it turns out to be this. So this is a little bit of a black box, but it's just computation. Oh, that's another term. Okay, so generalities bring you down to G2, and then some specific arguments allow you to be coming down to G1, a bit more manipulations, and you get down to this kind of function. Okay, these are concrete high school mathematics, but they take some time. Some determinants and things like that. Anyway, so you come down to this. You can see the constant lambda is beginning to appear over here, right? And here you have some image of some Heck operator on some function. So the claim is that this is exactly, I was going to do this computation in lecture 1. If you look at the formulas, and that's why I wrote them, this is exactly T12 minus lambda I applied to this function. Identity xi y to the r minus I. It would be nice if there were 2-3 extra minutes, and I could have gone back to lecture 1 and completed the circle. You look at the formula for T12, there it was a sum of something, right? 1, 0, p lambda p, and those were the representative matrices. You apply them to, right? So just a little check from lecture 1. So remember, this thing is mapped to the characteristic function of PCP, right? So T12 of this thing will map to T12 applied to the characteristic function of C. Characteristic function of T12 applied to that, there's some formula for it, and you get exactly this. This is just a easy computation from lecture 1 using the formulas in lecture 1. So that's great now, because we see that this thing dies in the Banach space, right? It's congruent to 0 1 pi times the lattice. This was congruence was 1 pi times the lattice. So this function is dragging, so to speak, these kinds of functions to their death. Okay? So that map from induction a to the I d to the r minus I to f2I to I plus 1, it factors through T12 minus lambda I. So this is the generator of the a to the I d to the r minus I part. In other words, okay, maybe yeah. So let me just say that. So this computation I want you to do, but it's there in the notes, it's 3-4 lines. Thus, induction a to the I dr minus I, compact induction from I z to G to f2I, 2I plus 1 factors through induction I z to G of a to the I d to the r minus I, modulo image of T12 minus lambda I. Okay, so we're almost there. You can also check that the T minus 1, 0 dies. I think during this conference, this part of the argument has been shortened. There was a slightly longer argument for that, but Nananbhadan made some comment. The two Anand stopped. And I think this part of the argument is now much easier. And this is exactly to pull out an AD to the I, which is omega to the I. This is pi r minus 2I lambda I omega to the I. Pull out an AD to the I, which is a determinant, right, like that. Okay, so this is the way this works. Starting with from a function, you come down to G2 or G1, G3, G2, G1, write it as the image of a Heck operator, and then show some natural map factors through the image of a Heck operator. But those are exactly these kinds of building blocks of 1P representation. So you know what the lattice is, because you know some subquotients are of this form, reduction of the lattice is, because some subquotients of it are of this form. Then you invert these by overhauling 1P LLC to get the shape of the representation and get the name here. Okay, so sorry for going 7 minutes over time. I think we have a very short